Hello everybody, welcome back today. Today we're going to be doing the question balance a binary search tree. So let's get into it. Alright, so let's get into the iPad explanation here. So our input is a BST that is not balanced. And by definition, balanced is basically you take the absolute value of the left height, so I'm just going to write it as left h, minus the right height, right? And we want to make sure that this absolute value of this difference is less than or equal to 1. So essentially it's either 0 or 1. So what that means is like if I take the right subtree height on my input right now, it's 3, and my left subtree height is 0. 0 minus 3, and the absolute value of that would just be 3. So it's actually not less than or equal to 1. So this is not actually a balanced binary search tree. So what that essentially means in terms of like in general, not the math, is that you want to have at least like the equal, roughly around equal amount of nodes on the left and the right side. And that's going to be a very important key for this question. So we can see in our output, and I have two outputs here. Basically, the question tells us that you could return any of them. So they don't really care which binary search tree you return. They just want a balanced one, right? So basically, here, we know that this is balanced because if you look at this input, right, the right subtree height is 2, and then the left subtree height here is 1, right? And that difference is at most 1, right? So you can see there's roughly about the same amount of nodes on the left and right side. Same thing here. This is 2, and this is 1, right? And so we see the difference again is less than or equal to 1. So we want to make it balanced. Well, how do we go about doing this, right? Well, we need to think about what we're given. We're given a binary search tree. What is like a key thing about a binary search tree? Well, one of the biggest key factors about a binary search tree is like whenever you take an in-order traversal of a binary search tree, right, it's always going to be sorted. And we know this just from like the definition of how a BST works. The BST says that, whenever you have a root of a node, right, anything to the left of that node is going to be smaller than it. All the elements are going to be smaller. And anything to the right of that node, everything is going to be bigger than that root node. So since we know that fact, that means by definition, and you guys can kind of search this up if you want, like about the definition of BST and stuff, but like if you draw it out, if you take an in-order traversal ever of a BST, it will always be sorted. So this gives us a sorted array, right? So let me just take our input example, which is if you do the in-order traversal of this, you'd get 1, 2, 3, and 4. Well, we have this, but this doesn't really tell us, like, how is this going to be balanced, right? Well, remember what I told you, right? You want to have a balanced BST is basically that there's roughly equal amount of nodes on the left and the right side. How do we ensure something has split in half? Well, I'm going to take the middle, right? So let's think about that. Let's say I take the middle here, which is 2, right? And I look to everything to the left of it is going to be on the left side, and everything to the right of it is going to be on the right side. Well, okay, I have these two subarrays now. Let's do the middle concept again. Well, on the left side, I only have one element, so that is my middle. So again, 1 is going to be on the left side, so this is going to be connected like that. Now here, 3 and 4, the middle is going to be 3, so this is the same. And then I break again, right? This is my right side. So now this is 4, right? So you see that this is exactly what this is. Right? And let's do another example just to make this clear. And you can kind of see how this is sort of looking like a recursion question, right? And it is, right? A lot of these tree questions will involve recursion. So here, let's say middle again, right? 4. So that's our 4. And then this is now my left side. This is my right side, right? I'm going to label it like this, left and then right. Now, I'm going to do the middle concept again. So I have 2 and 6. So 2 is on my left side, so that's my left subtree root node. And then my 6 is my right subtree root node. So we have 2 and 6, right? And then we split again. So this becomes the left of the 2, and this becomes the right of the 2. The 5 becomes the left of the 2, and the 7 becomes the right of the 6. And sorry, 5 is the left of the 6, right? So let's just draw that out. So you see that this is sort of what's happening here. And you see that this splitting in half is always ensuring that it's balanced. And this is actually perfectly balanced because they both have the same height. So there's the same amount of nodes on each side. So this middle concept works just because of the definition of how balanced works, is because you want to basically ensure that there's roughly the same amount of nodes on each of the sides, right? So that's the concept. One more note that I would like to add is you might have, if you know a lot of data structures, you might have heard of AVL rotations. And this is basically stemming off of AVL trees, which is known as a self-balancing binary tree. And it basically uses rotations of nodes on different points to balance the tree. Now, if you don't know about it, don't worry about it. It just makes it a lot more complex. But yeah, like I was going to say, this is going to work, but this is a complex code, right? And also, I believe the time complexity is a little bit worse here, just due to the fact of the BST part, right? So the time complexity is a little worse here. And also, it's complex code. It's going to be harder to write in an interview. So there's really no point of doing this. It's much better to use like is kind of like a semi-greedy approach, right? Now let's talk about the time complexity. Now I'm going to do this in a different color. First, we need to have this in-order traversal array, right? So first things first, it's going to take a big O of n, right? We're always going to go through all the nodes to get that in-order traversal. Now, next comes building a tree, right? So I'm just going to write this here, building the tree. It's going to be, we're also going to call this function build tree. Well, if you think about it, we're splitting in half, but we're essentially going through all the tree nodes because we're constructing them, right? We're making sure that they're actually connected to their previous parents and stuff like that. So this is also going to take a time complexity of O of n, right? Because we're going through all of the nodes. So in total, our time complexity will be O of n plus O of n, which is again just going to be, it's going to simplify basically to O of n, right? Because we don't care about the constant factors and stuff like that. And then the space complexity will be O of n as well, because we're going to be using recursion. So this is going to be the auxiliary stack space, right? So this is always going to be O of n. And this is pretty much the best time complexity you can get for most of the tree questions. Sometimes you can get O of 1 space complexity, but for this one, this is going to be the best. So let's get into the code, and I can explain it more there too. All right, so let's get into the code here. So I'm going to be doing this again in C++, but you can do this in any language. The concepts will transfer over. So the first things first, we need an in-order traversal, right? We said this, we want an in-order traversal, and in my case, I want an in-order traversal with all of the nodes, so it's going to be in a vector. So I'm writing a void function called in-order traversal, and I'm essentially going to pass it the tree node so we can actually traverse through it. And I'm going to pass it a vector, which is going to store the int values of these nodes by reference. So why I'm passing it by reference is to ensure that whenever I call this function, it's actually updating my vector, which is going to be in my balanced BST. So I'm going to also initialize it here, but basically I'm going to call it in order. And when we call this in order traversal and we pass it the root and the in order, it's going to actually update this vector and not create like a copy of it or anything like that. So that's why we're passing it by reference. So in order to do in order traversal, first thing, our base case is like if the root is null pointer, then we just return, right? And the whole point of in order is we go left, root, and right. And I have a video on like traversals of trees, so I'm going to put that link in the description if you want to check it out and go into further depth. But yeah, essentially we basically go to the left here, right? We want to traverse left. And then once we are done traversing left, we come back to that node, and this is where we add it to our vector, or essentially do any tasks. But in this case, we're adding it to our vector, so it's going to be root val, that's the int value. And then we do another in order traversal to the right. And this ensures that you do it in order. So left, root, and right, right? So that's how it's going to be there, and that's why it's going to be sorted. So, oops, I wrote left here. So this should be right. And then this should be our in order traversal. And the next thing is we want to build the tree, right? We have this vector, now we want to build it. So I'm again going to call it another function called build a tree. And this one's actually going to return the node itself. It's going to return the root of the new tree. Because if you think about it, once the recursion's over, we're going to be at the root when we backtrack. And that's what we want to return. So basically all this one's going to get is going to get that vector that we just created for the in order. And then it's going to get two ints, which is going to be left and right. This is going to help us determine the mid, right? So, oops, I cannot spell. But yeah, this is going to be the vector and essentially, or the function, and we're just going to call it. We're going to call it, and we can return this, in fact. We can just straight up return it because essentially we get the in order, and then we get 0 as our left because that's the left index, and the right index will be the in order size minus 1. So that's the right, like the rightmost index of that vector. And so how we want to do this is, first things first, if our, essentially we want to ensure that left is not past right. So what I mean by that is like, if left is ever greater than right, then we know that we're past the middle, right? We're past the middle, so we don't need to do anything anymore. And that's going to happen just because of the fact that whenever we're finding the middle and we're going to keep shifting it around, there's going to be a point where they cross, and that cross is when we want to end, because that means we've gone through all the nodes. So that's what we want to make sure we have. So if ever left is greater than right, we just stop. We essentially return null pointer. And that's going to happen when we're at the child nodes. Like at the child nodes, when they go left, they go right, it's going to cross over because there's technically no in order, like null node in our in order traversal. So that's when this is going to crossover is going to occur. So next, what we want to do is we know that the middle, we want to basically calculate that middle. So first thing, middle will be left plus right divided by 2. This is one way to do it. Another way to do it that you'll see a lot of times, a lot of people do is this. And this is to ensure that you don't overflow the integers. So if left and right are like very large, this could overflow. And in our case, they're 10 to the 4, 10 to the 5, so they're really not going to overflow. But yeah, in some cases you could. And that's because when you add, you could cross that barrier, but if you subtract, you're not going to cross like the the barrier for like the max int and stuff. So this is another way to do it, but this is just the simple way, so I'm going to keep it that way. And then our tree node, remember we said the middle node is going to be the like one of the roots of the subtree. So essentially I'm going to call it node, and then I'm just going to say it's the in order middle, right? But this is an int, so basically we're going to create a new tree node here. So and pass it this, and LeetCode tells us that the constructor, one of the constructors, takes an int. So this is essentially what this is doing, and we know that we're going to make recursive calls to the left. So how this is actually done is you do node left, and then you make it equal to a recursive call. And since our function returns a node, it will actually return the left node that we specifically want. So essentially, we're going to do in order. And since this is saying that everything from mid -1 is on my left subtree, our left stays the same, but our right is going to become middle -1, right? And then same thing here. This is going to be from the middle to the ends, right? So to the right. And I'm going to copy this function. And this basically starts at middle +1, right? That's going to be your new left, and then the right side. So that's right. And at the end, we just return this node, essentially. And this recursive call, this is essentially how it works, but you can kind of dry run this on different examples and see how once you get to the middle, it's going to create that new node, which will essentially get sticked here because we're going to keep calling it to the left until it returns null pointer. Again, keep calling it to the right until it returns null pointer. And then when we backtrack back, this is actually going to have the subtree that's going to keep going back and forth. And then until we get to that one subtree that is our root, and it's just going to return that new root of the binary search tree. So let's run this, make sure we don't have any compilation errors, anything that we missed out. And as you can see, yeah, we did something wrong here. One thing that we did wrong is that we didn't pass in these in order to that function that we have. So that's just a simple fix that should work. And yeah, as you see, we passed these two cases. Let's just submit on LeetCode, make sure we pass all the test cases that they have. Another thing I want to note is this is actually the problem of the day. So yeah, let me know in the comment section down below if you had any questions or any concerns about like the solution or anything like that. Another thing I want to mention is this LeetCode accepted thing, the beats whatever percentage. This is a very like scuffed metric on LeetCode because it very dependent on how many people are submitting this. And this is the problem of the day. There's like 100,000 people probably submitting this at a time, so this could be slow, but this is essentially the fastest solution. But yeah, again, like I said, make sure to leave a like, subscribe to the channel. Let me know in the comment section down below any other videos you want to see, but I hope to see you on the next one.